Okay, the topic of this talk originated from the 1930s papers of Einstein and Schrödinger and the 1960s paper of Bell. The issue involved two strange features of the Copenhagen interpretation of quantum theory, and these included macroscopic entanglement. States could exist in bipartite systems in which a subsystem could simultaneously occupy two macroscopically distinct states, the Schrödinger cat. There was also EPR steering, measuring the value of an observable chosen for one subsystem A could sometimes instantaneously affect the outcome for measuring the value of an observable in a second subsystem B that was spatially well separated. In addition, there was Einstein's question: does quantum theory, though agreeing with experiment, require completion via an underlying theory that determines the real physical values underlying the quantum probabilities? Well, in response, Bell introduced a so-called local hidden variable theory for the quantum states of composite systems. The states were referred to as Bell local states. The idea was that the hidden variables only depend on the state preparation process. It didn't depend on what the measurement choice was going to be. Essentially, hidden variables act like a classical phase space variables, and in the general version, they determine the probabilities of outcomes when the subsystem observables are measured. This is the locality feature. The local hidden variable theory provides predictions for inequalities involving results based on the mean values of pairs of observables from the two subsystems, generally referred to as Bell inequalities. So we can test whether the inequality predictions based on local hidden variable theory are consistent both with quantum theory predictions and with experiment. And it turns out that some Bell inequality violations show that local hidden variable theory fails. So does that mean that the quantum state must be described by a so-called local hidden variable theory? Well, looking at the mathematics of it, the quantum theory and local hidden variable theory probabilities for the measurements of the observables omega A and omega B for the two subsystems with outcomes alpha and beta are shown here. You'll notice in the quantum theory expression, it involves a projector onto the space of eigenvectors for operator omega A that have eigenvalue alpha. And rho is the density operator specifying the preparation process C of the quantum state. For the local hidden variable theory, the hidden variables lambda are determined with a probability shown here for the process C. And in the probabilistic form of local hidden variable theory, the hidden variable theories determine the local subsystem measurement probabilities for the classical observables omega A, for hidden variable lambda, and these are then combined using classical probability theory to determine the joint measurement probabilities. Mean values, there's the expressions for the quantum mechanical and the local hidden variable theory mean values. And for example, the quantity mean value of omega A of lambda is the mean local hidden variable theory mean value for the measurement of omega A when the hidden variables are lambda. And a classic example of such an inequality is the CHSH Bell inequality for a bipartite system where the outcomes alpha and beta are restricted to just two values, +1 and -1, and they involve two measurement choices for each subsystem, such as omega A1 and omega A2. And this is violated for the singlet state of two spin-half systems, the state being shown there, for the choices where, for example, omega A1 is the Z component of the spin, omega A2 is the X component of the spin, and similar things for the B. In this case, you find the quantity S is not less than or equal to 2. In fact, it's 2 times root 2, so it's root 2 times higher. So that means that in some Bell inequalities, the CHSH Bell inequalities, the quantum states were found in a microscopic bipartite system where the local hidden variable theory inequalities were violated. And so the failure of Bell local hidden variable theory was predicted. And then there were later experiments by Aspey and Zodiger, which agreed with quantum theory. So this is sufficient to rule out local hidden variable theory accounting for quantum theory in general. This is a very important quantum foundations issue, which got implications, of course, for quantum technology in things like secure communications, quantum information processing, etc. Well, we can't forget about quantum entanglement and EPR steering. Bell locality violation also implies that EPR steering and quantum entanglement both occur. However, Werner showed that quantum entanglement or EPR steering can also occur for some Bell local states. And although this talk is focused on tests for Bell locality violation, Bell tests for quantum entanglement or EPR steering are also important. It turns out the violation of other Bell inequalities for local hidden variable theory involving what are called local hidden quantum states, an idea from Howard Weissman, are used to determine whether the state shows quantum entanglement or EPR steering. I also should mention that there are other types of inequalities for multipartite systems. We've talked mainly about bipartite, such as in the case of GHZ states, also for measurements at 3 different times, the so-called Leggett-Garg inequalities. Okay, so the point is that the quantum states can be divided into entangled or separable states. It's one division of the quantum states, but they can also divide it into the Bell local and the Bell non-local states. But these categories actually overlap with each other. Let's look at the separable states. For separable states, you prepare the subsystems A and B in the quantum states row AR, row BR. So the combined state row AR cross row BR occurs with a classical probability PR, and the state is then described by the density operator shown here, and the measurement probabilities are given by that expression. So you can see then that the joint outcome probability actually is in the form of a Bell local hidden variable theory form. Here, so that means basically that all separable states are Bell local. The quantity R is a bit like the hidden variables, so Bell non-local states must be entangled. However, what you see is that for Bell local states which are separable, both subsystems are associated with a quantum density operator. And that led Howard Weissman to introduce the idea of a so-called local hidden quantum state. Well, Bell local states for bipartite systems can in fact be divided into 3 disjoint categories, depending on whether there's 1, 2, 1 or none of the subsystems being associated with a local hidden quantum state. So the local hidden quantum state, rho C of lambda, of course, has to be a possible quantum state for that subsystem and must comply with things like super selection rules of no coherences between states for differing particle numbers. That's in the case of massive particles. And there's the formula for the outcome probability in hidden variable theory for the 3 categories. And you notice that there is a Q indicating in the particular cases that a subsystem measurement probability is determined from this local hidden quantum state. Okay, in the case of 2 modes, we can introduce these things called spin operators, shown here. And you see, of course, that the category 1 states are the same as the separable states, since both subsystems probabilities are given by quantum expressions. So that would mean that violation of inequalities based on the category 1 states will show that quantum entanglement occurs. And that, and a particular example of such a Bell test is the spin squeezing test for two-mode entanglement, which says that either the variance of the x component of the spin or the variance of the y component of the spin is less than a half of the magnitude of the mean value of Sz. For category 2 states, only one subsystem, which is B, is given by the quantum expression involving a local hidden quantum state density operator. Here you see that no EPR steering of B by A occurs because the outcomes beta for measuring omega B will depend only on the local hidden state density operator rho B of lambda, and they won't have anything to do with the outcome of what happened in A, omega alpha and omega A. So that means that the violation of inequalities based on category 2 states will tell you that you've got EPR steering of B outcomes by A measurement outcomes. And that can be written in the form of the generalized Hillary-Zuberi planar spin variance test for two modes EPR steering. And that tells you that the sum of the variances of Sx and Sy have to be less than this particular quantity there. So what about the test for Bell non-locality itself? Of course, for category 3 states, neither subsystems probabilities are given by a quantum expression. There's no local hidden quantum state. So that means that inequality violations based on the category 3 states will tell you that Bell locality cannot apply. And the example I've already given is the CHSH Bell inequality, which is derived from that. So thus, Bell non-locality is shown by violations of inequalities based on this expression here, where these are classical probabilities and depending on hidden variables. Might be worth pointing out that there is actually a fourth category of states, which are the Bell non-local states, in which the joint outcome probability is given by an expression like this. And you notice here that there's no separate outcome probability depending on the hidden variables for each of the subsystems. So there's no locality here. So what would happen if we could derive a violation of inequalities based on category 4 states? I think that would show you that a non-local hidden variable theories would also fail. So this is a big question. Can a contradiction with quantum theory be found for category 4 states, which is what I'm trying to work on at the moment. So there's a diagram of the overall scheme, which is in one of my papers on the subject. So coming back to the issue of macroscopic non-locality, of course, experimental realization of quantum systems on a macroscopic scale is now possible, such as in Bose-Einstein condensates, degenerate Fermi gases, also certain optomechanical systems, also superconducting flux qubits. And you might find that local hidden variable theory and quantum theory might actually agree in such macroscopic systems. Maybe the decoherence effects could effectively wipe out the quantum behavior, and so quantum theory would not be needed. So there is a current interest in finding cases of macroscopic violations of the Bell inequalities, including the local hidden variable theory violations to prove Bell non-locality, which is the focus of this talk. There's a review on this, not with my name on the article, but it's a very good review written by colleagues at Swinburne. And anyway, that's worth having a look at. So I'll now just sort of briefly mention a few cases of Bell non-locality for macroscopic systems. There's an earlier one due to Merman back in 1980. He considered two large spin systems, S, with the spin quantum number S, in this singlet state, you can derive an inequality involving spin components along unit vectors A, B, and C. And this was violated for 3 distinct coplanar unit vectors where the A and the B make an angle pi over 2 plus theta with C and pi minus 2 theta with each other, provided theta is in that range. Now that's a pretty small range around 0 if S is a big sort of number, like it's a big spin system, so it'd be pretty hard to actually do an experimental test. But nevertheless, macroscopic Bell locality is definitely predicted, but no experimental test has yet been done to my knowledge. There's another one by Peter Drummond, which similarly also doesn't yet have an experimental test, and again would be difficult to do. I'll move on to some work done by Margaret Reed et al. Back in 2002. She derived, this was developed from the CHSH inequality, a bipartite case with spin observables for 2 subsystems. And she introduced spin operators that depended on theta or phi, depending on whether you're dealing with subsystem A or B. And they considered states with spin quantum numbers SA and SB. So the outcomes in this case would range from minus SA to plus SA, or minus SB to plus into SB. And you could divide the outcomes into positive and negative bins. And from that, you can derive a Bell-type inequality shown here. And that's violated for this state here for certain ranges of the angles. And so basically, again, you have macroscopic Bell non-locality for large N. And I believe there has been an experimental verification of this. I'm more interested recently in the so-called CGLMP Bell inequalities. That's Collins, Geeson, Linden, Massar, and Popiesco. And here one is talking about a bipartite system with 2 observables per subsystem. And so the local hidden variable joint probability that's of interest is this one here, which is just abbreviated as C of JKLM, where the outcomes are listed as JKLM respectively. The outcomes are actually chosen to be the same. They are numbers from 0 up to D minus 1. So there's the same number of outcomes for each observable D. And then you can derive the local hidden variable theory from classical probability theory for the combined outcome as given by this expression here. And it's then straightforward to show that the probability for joint outcomes for one observable for each subsystem will satisfy the local hidden variable theory conditions. And there's a typical case for the outcomes for the observable omega A1 and omega B1, and you see that's in the Bell local hidden variable theory form. Well, Bell inequalities can be derived for involving the probability that the 2 observables involve the same outcome, written as P of omega A1 equals omega B1, meaning the outcome for A1 is the same as the outcome for B1. Or the other case is where 2 observables have outcomes which are shifted, such as where the outcome for B1 is the outcome for A1, A2 plus 1. And there's a typical CGLMP Bell inequality showing that that quantity there is less than equal to 3. Of course, these are done in 3 different sets of experiments, measuring A1 and B1 together, or measuring B1 and A2 together, etc. And that's actually violated for this state where the observables have eigenstates, eigenvalues K and L, and the eigenvectors are given there. So here, macroscopic Bell locality occurs for D large, and there's been an experimental variation up to D equals 12 in this particular case. I won't talk about that one or that one, and I think I'll skip over the two multi-partite cases in view of the time, but there are Bell-type inequalities there as well. Let's move on just to the final two cases. One is the case of two macroscopic optomechanical oscillators, each containing 10 to the 10 atoms, which are involved also with two optical photonic modes. And as CHSH Bell inequality is violated by 4 standard deviations and shows that Bell non-locality occurs in this macroscopic system. The next one is the case of two-state macroscopic superconductor circuit, where the magnetic flux is either clockwise or anti-clockwise, so the outcomes can be written as +1 or -1, but now they're going to be measured at 3 different times. And there one can use the so-called Leggett-Garg inequality, which is that, and a violation of the inequality by Ni et al. Shows that the flux state for a macroscopic system can be in a coherent superposition of clockwise and anti-clockwise states, which I think is highly non-classical. Well, that's about it. Here's a summary of basically what I've told you. So first part, I've covered the historical background to local hidden variable theory. I've defined it and discussed Bell non-local states that violate Bell inequalities. I've talked about the relationship between the categorization of states as entangled versus separate, but as compared to Bell local versus Bell non-local. And I've identified 3 categories of Bell local states, one being EPR steerable, along with the Bell non-local states. The other 2, one being separable, being EPR non-steerable. And in the second part, I discussed macroscopic systems based on cold quantum atoms and other systems, and gave examples of bipartite systems exhibiting macroscopic Bell non-locality. And there's a lot of references. I've got copies of these references if anyone is interested in having a copy. And I'd like to also finish up by mentioning the researchers at Swinburne University who are involved in this sort of EPR steering, Bell non-locality work. It's in the Centre for Quantum Science and Technology Theory. The director is Professor Margaret Reed, and the other leading researcher in there is Professor Peter Drummond, both FAAs. There's me, and there's Laura, who's now actually gone back to Mexico. Runyon Tay is a postdoc. Choggy is now back in China. Bogdan is now in IT somewhere. Ria Joseph is now at Deakin University, and he's just about finished his PhD. And I thank you very much for your attention. I thank the organisers for the opportunity.
Hey, wonderful talk. So we have time for one quick question. So if you can get the mic to the front.
Trust him.
Well, the slides were really involved, and entire careers are devoted to these issues. See, from
Sorry?
Entire careers are devoted to these issues, as seen by the references and the number of people shown here. And I'm not one of these people working in the field, so excuse me if this is a really stupid question. What alarmed me was this existence of category 4 states, by using which you can also invalidate non-local hidden variable theories.
That's right.
So I want to understand this better. Is there a way to definitively show experimentally that quantum mechanics cannot be explained away by a non-local classical hidden variable theory?
Well, that's what I'm trying to work on at the moment, and I may be able to tell you the answer in a few months' time. I want to see if I can derive a Bell-type inequality based on category 4 states and show that there's a violation between that and a quantum mechanical state.
So there's still a possibility that
still-
quantum mechanics is actually a classical non-local hidden variable theory. This is still a possibility.
It's possible. There's work done. Some work was done on this by Leggett back in about 2003, but hardly anyone has taken an interest in this question as far as I can tell. And certainly there's been no experiments that I know of. But it's an excellent point.
Really interesting. Thank you so much.
Okay, please join me with thanking Bryan again.
Thank you.